Welcome colleagues in the room, and welcome colleagues who are joining us online. If you're joining us online, welcome to the virtual IAS, and if you're here, welcome to the home of the IAS at International House. My name is Marcia Meskimen. I'm the director of the Institute of Advanced Studies. I'm going to give a few words of housekeeping, and then we're going to get started with this very exciting seminar today. Housekeeping, if you are joining us online, you will note that this webinar has a Q&A and a chat function, and you are very welcome at any point to ask questions in that chat function or in the Q&A, and they will be monitored, and we will make sure that they go in at the end of the seminar to have your voice heard as part of the discussion after the paper. What I would say is we don't keep anyone's data, however, so we are recording the talk, but the talk only. So we will not be recording the conversation or the dialogue or anything from the chat. And then shortly after the seminar is over, usually within at least a week, if you are interested in being able to view the talk again, it will appear in our video library on the Institute of Advanced Studies YouTube channel on our site. So please do actually feel welcome to review it. For those who are joining now, to get started more formally, it is my great pleasure to welcome Professor Zahoor Farooqi, who is coming to us from the School of Chemistry at the University of the Punjab. And we've had a wonderful conversation about the beautiful building on the slide. So yes, that is his university. And yes, we are all extremely, extremely envious of that beautiful place. Dr. Farooqi is a very esteemed colleague in the field and has a wonderful track record of awards and research publications. And he is here being hosted by my colleague, Professor Joran Vladislavich, who is going to be giving the introduction to Dr. Farooqi's work. They've been working together now for some 2 years and have an ongoing collaboration. And so we were really delighted to hear about this work because it's part of a much bigger package of research. And we are really hopeful that through a variety of links, it will also become something which is ongoing, and we'll hear more about it in future. So if I could turn to you, Doran.
Thank you very much, Marcia. It is my exceptional pleasure to introduce today and to welcome today Dr. Zahoor Farooqi, who is working as an associate professor in the School of Chemistry of the University of the Punjab, Lahore. He worked as a research associate also in the City University of New York from January 2009 to March 2010 during his PhD studies. He also worked as a honorary research fellow in the Department of Chemistry of the University of Liverpool from 2018, and also he was a visiting staff member in the Department of Chemical Engineering in Loughborough in 2022. Professor Farooqi published more than 140 research articles, which have been cited so far more than 4,000 times with an H index of 40. He will also served as an editor of journal Gels, and also due to his research contribution in the field of chemical sciences, he is named in the world's top 2 highly cited researchers, which is a list prepared by Elsevier. He appeared in that list in 2021, 2022, and 2023. He also got prestigious awards for his science in Pakistan, and also so far he mentored more than 30 PhD students in Pakistan. His area of research is polymer science and microgels loaded with inorganic nanoparticles. This kind of microgels can be used in various biomedical applications, environmental applications, and catalytic applications. And we will have a pleasure to hear about all these developments in today's talk. Please, Dr. Farooqi, please deliver your lecture.
Thank you very much. Thank you very much, Dr. Goran, for introduction. I am also thankful to Professor Marsha and her team for supporting me under the IAS Open program. As Dr. Goran told, our group is working in smart polymer microgels, their fabrication, characterization, and their application in environmental and catalytic field. So first of all, I am going to briefly describe what are microgels. Gel is a cross-linked polymeric system filled with a suitable liquid like this. If the liquid present inside the network is water, then the cross-linked polymeric network system is known as hydrogels. Hydrogels can be further classified into different classes depending upon the size of polymer network. If the polymer network is extensive and the size of polymeric network is more than 1 millimeter or more, then these hydrogel systems are known as a microgels. But we are actually working in the field of microgels. Microgels, in fact, is a colloidal dispersion like this. And we, in fact, have a cross-linked polymeric particle of colloidal size, which are dispersed in an aqueous medium. So the aqueous dispersion containing the polymeric particle is just like this. As a whole, this system is a sol because the solid particles are dispersed in liquid. But if we focus on a single particle, it is a gel system because liquid is entrapped in the polymeric network. So if we have the particle size in the range of 0.1 to 100 micrometer, then the cross-linked polymeric particle are known as microgels. If we have the particle size in the range of 1 to 100 nanometer, then these cross-linked polymeric particles are known as nanogels. So the microgels can be further classified into various classes on different bases. For example, on the basis of morphology, microgel particle can be classified as homogeneous microgel particles and core shell microgel particle. In homogeneous microgel particle, we have almost same structure throughout the network. But in case of core shell microgel, we have a different material in the interior of microgel particle, and the cross-linked polymeric network is different from the interior of microgel particle. So the core shell microgel particle, in the core shell microgel particle, we have a polymeric core, which may be a solid polymeric core and a cross-linked polymeric network around the core. The microgel system can be further classified on the basis of nature of cross-linking. If the cross-linking is chemical, then the microgel system are known as chemically cross-linked microgel system. If the cross-linking is a physical bonding like van der Waals forces or hydrogen bonding, then the cross-linked polymer microgels are known as physically cross-linked microgel system. The microgel system can be further classified on the basis of their responsive behavior. If the microgel particle have ability to change their size in the presence of some external stimulus like temperature, pH, and ion strength of the medium, then the microgel system is known as smart polymer microgel, intelligent microgels, or responsive polymer microgels. The responsive polymer microgels can be further classified on the basis of the stimulus like temperature responsive microgels, pH responsive microgels, or ionic strength responsive microgel, or glucose responsive microgels. For example, if we have a temperature responsive microgel, These are those microgel particles which are hydrophilic at low temperature and become hydrophobic at higher temperature. That is why at low temperature, the microgel particle exists in swollen state. They have a large particle size, but when we increase the temperature, the particle size suddenly decreases. This behavior of the microgel system is known as temperature responsive behavior of the microgel system. The temperature responsive behavior of the microgel system can be explained on the basis of variation of hydrodynamic radius or size of the microgel particle with temperature. We can measure the size of microgel particle dispersed in a liquid using dynamic light scattering techniques. And then we measure the hydrodynamic radius of the microgel particle as a function of temperature. It has been noted that initially the size or hydrodynamic radius of the microgel system remain constant and then suddenly decreases and again become constant. This responsive behavior can be explained on the basis of functionalities present in the network of polymer microgels. Usually, the temperature responsive microgel are based on N-isopropyl acrylamide based monomers and N-isopropyl methacrylamide based monomers. You can say we have a functionality amide group in the network in both monomers. These groups have ability to form a hydrogen bond with aqueous molecules or water molecules. So this group is in fact hydrophilic, but the isopropyl group and the polymer backbone is hydrophobic. So at the same time, the temperature responsive units have hydrophilic units and hydrophobic unit. The hydrophilic unit can form hydrogen bond at low temperature, but when we increase the temperature of the medium, the hydrogen bonding is broken and the polymer interaction becomes stronger and polymer solvent interaction becomes weaker. As a result, the size of microgel particles suddenly decreases at a particular temperature. The rate of change of hydrodynamic radius with respect to temperature is maximum at a particular value of temperature, which is known as volume phase transition temperature. The value of volume phase transition temperature depends upon various factors. For example, N-isopropyl acrylamide based microgel have the value of volume phase transition temperature equal to 32 degrees centigrade, but the N-isopropyl methacrylamide based temperature responsive microgel system have the value of volume phase transition temperature equal to 44 degrees centigrade. So the value of volume phase transition temperature depends upon the nature of main monomer used, the nature of co-monomer used. For example, if we use a hydrophilic monomer, the volume phase transition temperature can be increased. If we use some hydrophobic co-monomer, the value of volume phase transition temperature can be changed or can be decreased. So value of volume phase transition temperature also depends upon the solvent of the medium solvent system. Value of volume phase transition temperature is also affected by the pH of the medium. We have reported various microgel systems which have temperature responsive behavior. A typical temperature responsive microgel system reported in Polymer International is shown here. Actually, we fabricate a poly-N-isopropyl acrylamide, and acrylic acid-based microgel system, and we modify this microgel system to have a phenyl boronic acid into the network, and we measure the value of hydrodynamic radius of the microgel systems at different pH values. It was noted that the value of hydrodynamic radius initially remain constant and it decreases at a certain value of temperature, which of course is known as volume phase transition temperature. We can see the value of volume phase transition temperature can be tuned by changing the pH of the medium or by changing the feed composition of microgel system. A typical TEM image of poly-N-isopropyl acrylamide phenyl boronic acid microgel system is shown here. The particle formed are nearly spherical, but do not have exactly similar size. There is some polydispersity in the microgel particle system. Similarly, if we have some functional group inside the network which has ability to respond the pH of the medium, then the microgel system are known as pH responsive microgel system. For example, if we have carboxylic acid groups inside the network, and when we increase the pH of the medium, the deprotonation of carboxylic acid groups occur, and the neutral microgel particle will change into negatively charged microgel particle. There will be an electrostatic repulsion between these functionalities, which causes extension in polymeric network. As a result, the particle size will increase with increase of pH of the medium. Similarly, if we decrease the pH of the medium, the protonation of carboxylic acid groups occur and the particle size is decreased. Similarly, we can measure the change in hydrodynamic radius of the microgel particle as a function of pH of the medium using dynamic light scattering. The value of hydrodynamic radius actually initially remain constant, then increases suddenly, and then again the microgel particle size become constant. Actually, the value of pH at which rate of change of hydrodynamic radius with respect to pH is maximum is equal to pKa value of co-monomer used in the microgel system. So the microgel system has ability to swell or deswell by changing the pH of the medium. We have reported a various pH responsive microgel system in different journals. Similarly, if we have some specific functionality in the network which has ability to form a complex with glucose, we can obtain the glucose responsive microgel system. For example, if we have the phenyl boronic acid based functional groups in the network, if the phenyl boronic acid based functionalities are present in aqueous medium, they actually exist in aqueous medium in a dynamic equilibrium with uncharged form and charged form. If we increase the pH of the medium, this equilibrium can be shifted in forward direction. Moreover, the charged phenyl boronic acid functionalities has ability to form a complex with glucose molecule. As a result, the glucose, by forming the complex with charged species, can shift this equilibrium in forward direction. As a result, the number of charge group inside the network will increase. There will be an electrostatic repulsion between these groups, which causes extension in the network. As a result, the particle size will increase with increase of glucose concentration. We have reported various glucose responsive microgel systems. For example, you can see the value of hydrodynamic radius as a function of glucose concentration under various feed composition and pH values. You can see the value of hydrodynamic radius of the microgel particle increases with increase of glucose concentration. Moreover, the dependence of hydrodynamic radius of the microgel system is also a function of feed composition as well as the pH of the medium. Although the 4-vinylpyridine is not a glucose responsive moiety, but it can increase the glucose responsiveness by donating the electron density from electron-rich nitrogen atom to the electron-deficient boron atom present in the network. So in this way, we can obtain a microgel system which has ability to respond to the glucose concentration In this way, we are able to measure glucose concentration in the blood, and we can also provide the basis for self-regulating insulin delivery system for the sugar patient. Due to their responsive behavior, like pH responsive behavior, temperature responsive behavior, glucose responsive behavior, microgel system have a potential application in various fields, including pH sensing, temperature sensing, glucose sensing, insulin delivery, nanotechnological field, catalysis, and adsorption. I am going to just describe few applications of microgel system reported by our group. We actually used free radical precipitation polymerization method to form a microgel system. We simply used monomer, comonomer, and cross-linker for the fabrication of microgel system under nitrogen atmosphere around the temperature 70 to 80 degree in the presence of some suitable surfactant. We used some initiator to cause the polymerization in the network, and we can easily obtain the microgel cross-linked polymeric microgel particles by using free radical precipitation polymerization. And then these microgel particles can be used as a microreactor to fabricate metal nanoparticle into the network. For this purpose, we usually have a carboxylic acid groups in the polymeric network. The strategy is that initially we increase the pH of the medium. When we increase the pH of the medium, the carboxylic acid groups get deprotonated, and the microgel system is changed from protonated form to deprotonated form or negatively charged microgel particle. Then we can add a salt solution, metal salt solution into the network. Due to electrostatic attraction between negatively charged functionalities of microgel system and positively charged metal ions can easily move or diffuse into the network. Then we used some reducing agent to reduce the metal ions loaded into the microgel system. And we can convert the metal ions into metal atom, which aggregate together in each voids to form metal nanoparticle inside the network. These microgel particles are actually is a very fascinating material, because we have the properties of both inside. We have the properties of inorganic material like metal nanoparticle, and we have a properties of the polymeric network. Therefore, this microgel system containing the metal nanoparticle is known as hybrid microgel system. Actually, when we change the microgel into hybrid microgel system, the color of the dispersion is changed from milky white to some specific color, colored dispersion. So the color of the hybrid microgel system actually depend upon the size of microgel, size of the metal nanoparticle generated inside the network. We have reported this methodology for the fabrication and stabilization of various metal nanoparticles into the microgel system. Similarly, we can obtain a wide variety of hybrid microgel system. The microgel system containing the inorganic metal nanoparticles and the polymeric network. This material actually is known as a hybrid microgels, and we can have a variety of hybrid microgel system. For example, we can fabricate a homogeneous microgel particle filled with metal nanoparticles. We can have a microgel system with solid polymeric core and the shell containing metal nanoparticle. We can fabricate a microgel system containing a metallic core in the interior region of the microgel system and the polymeric shell. We can also have a hollow microgel system containing the metal nanoparticles. We can also have a microgel particle covered by metal nanoparticle. Our group has prepared almost all these morphology, and we have reported in literature. For example, we have fabricated polyanisopropyl acrylamide co-acrylamide microgel system using precipitation polymerization, and then this microgel system was used as a microreactor to load the silver ions into the network, and then we add a freshly prepared sodium borohydride solution into the microgel dispersion containing the silver ions, and we reduce the silver ion into silver atom to obtain a hybrid microgel system containing silver nanoparticle. We characterized this microgel system using dynamic light scattering, transmission electron microscopy, and UV visible spectroscopy. We were successful to load the silver nanoparticle into the microgel particles. But the microgel particle containing the silver nanoparticle were not exactly uniform, and there is some polydispersity in the polymeric network. Moreover, there is some aggregation of the silver nanoparticle on the surface of hybrid microgel particles. The peak shown in UV visible spectra in case of hybrid microgel is actually associated to the surface plasmon resonance property of the silver nanoparticle fabricated inside the microgel system. Moreover, the average particle size of the hybrid microgel was found lower than the pure microgel particle because the silver nanoparticle present inside the network act as a physical cross-linker, due to which the hybrid microgel particle have low value of hydrodynamic radius in comparison to pure microgel particle. We have reported various homogeneous microgel system loaded with different metal nanoparticle in different publications. Similarly, we were able to obtain the core shell microgel particle using two-step free radical precipitation polymerization. In the first step, we polymerized styrene in the presence of N-isopropyl methacrylamide, sodium dodecyl sulfate, and ammonium persulfate. In this case, ammonium persulfate was used as initiator, sodium dodecyl sulfate was used as a surfactant, and the N-isopropyl methacrylamide was used as one of the co-monomer to fabricate the polystyrene solid particle in aqueous medium. Then these solid particles were used as a seeds to fabricate a shell around seed nanoparticle by using N-isopropyl methacrylamide as one of the main monomer, N-methylene bisacrylamide as a cross-linker, and ammonium persulfate was used as initiator. Acrylic acid was used as one of the co-monomer to obtain a pH and temperature responsive core shell microgel system. We noticed that the shell has pH sensitivity and temperature sensitivity. The core shell microgel system was then used as a microreactor to load the silver nanoparticle in the shell region of the microgels. The sodium silver nitrate was used as a precursor salt, while the sodium borohydride was used as a reducing agent to convert the silver ions into silver nanoparticle. The resulting hybrid microgel system was used as a catalyst to reduce a variety of nitroarenes into aryl amines. The microgel system was characterized by transmission electron microscopy. You can see the images of polystyrene seed particle, core shell microgel particle, and the hybrid microgel particle. We have the silver nanoparticle in the outer region or on the surface of the core shell microgel particle. We have reported various core shell microgel system in our different publications. In the last step, we have seen that The core shell microgel particle can be obtained by a two-step free radical precipitation polymerization. But we have developed a methodology to obtain the core shell microgel system using single-step free radical precipitation polymerization. For this purpose, we used two different monomers with different functionality, with different reactivity. In this way, one of the monomer has ability to polymerize early. The other monomer has low reactivity. In this way, we can polymerize the highly reactive monomer in the same reaction mixture in the same reaction mixture, and then we can polymerize the less reactive monomer to form a core shell microgel system. In this way, we can obtain a core of highly reactive monomers, but we can have the shell of relatively less reactive monomers. In this way, we can obtain the core shell microgel system by a single step free radical precipitation polymerization. Then this core shell microgel system was used as microreactor to load the silver nanoparticle into the shell region of the microgel. The transmission electron microscopy was used to investigate the presence of silver nanoparticle in the shell region of the microgel system. The core is actually made a solid, highly reactive material, and it is a highly cross-linked network. Therefore, no silver nanoparticle were found in the interior region of the microgel system. We have used this methodology to obtain other microgel system with core shell morphology. For example, the core shell morphology of the microgel system is not only limited to the core of polymeric network. We can also construct some microgel system with metallic core in the interior region of microgel system. The methodology is slightly different from the previously described methods of free radical precipitation polymerization. In this way, we actually use a metal precursor salt, and we reduce the metal ions by a trisodium citrate in an aqueous medium using sodium borohydride as a reducing agent to obtain a very small particle of gold metal or gold nanoparticles. Then these gold nanoparticles were used as a seeds in the presence of PVP and ascorbic acid. The ascorbic acid actually was used as a reducing agent, and PVP was used as a capping agent, while the salt of gold solution was used to grow the gold nanoparticles. As a result, size of gold nanoparticle was increased. Then we used gold nanoparticle dispersion as a seed to polymerize the N-isopropyl acrylamide methacrylic acid in the presence of a suitable surfactant using N-methylene bisacrylamide as a cross-linker, and we used ammonium persulfate as an initiator to fabricate a core shell microgel with metallic core and cross-linked polymeric network. The hybrid microgel system was characterized by a transmission electron microscopy. You can see the gold nanoparticle, single gold nanoparticle in the interior of the microgel system, and we have a cross-linked polymeric network around the single gold nanoparticles. We have used the single-step free radical precipitation polymerization method to obtain a polyanisopropyl acrylamide co-2-hydroxyethyl methacrylate hybrid microgel system. The methodology is almost similar. We use free radical precipitation polymerization to obtain a microgel system. Then this microgel system was used as microreactor to load the silver nanoparticle in the outer region of the microgel system, and the resulting hybrid microgel was used as a catalyst for reduction of p-nitrophenol into p-aminophenol. The microgel system was characterized by a transmission electron microscopy, and the A and B images of are associated to the pure microgel system, while the C and D images are associated to the hybrid microgel system. We can see the silver nanoparticle were successfully loaded in the outer region of the microgel system. The resulting microgel system was used as a catalyst for reduction of 4-nitrophenol into 4-aminophenol. We initially conducted some controlled experiment. The reduction of 4-nitrophenol was carried out in the presence of pure microgel system, but no change in the value of absorbance or spectra of the p-nitrophenol was observed. In the second controlled experiment, we used sodium borohydride to reduce the p-nitrophenol, but sodium borohydride was not able to reduce the 4-nitrophenol into 4-aminophenol in the absence of core shell hybrid microgels. Similarly, we have also conducted another controlled experiment using p-nitrophenol as the substrate and the pure microgel and sodium borohydride, but we were not able to reduce p-nitrophenol by sodium borohydride in the presence of pure microgels. At the end, we use the hybrid microgel system as a catalyst to reduce the p-nitrophenol by the sodium borohydride, and we were able to reduce the p-nitrophenol into p-aminophenol. And this is the catalytic reduction spectra of reduction of 4-nitrophenol into 4-aminophenol. We can see the value of absorbance at 400 nanometer is actually associated to the p-nitrophenol, and the peak at 300 nanometer is actually associated to the p-aminophenol, which is a product. When p-nitrophenol is converted into p-aminophenol, the value of absorbance at 400 nanometer is going to decrease over the time, but the value of absorbance at 300 nanometer is going to increase, which indicate that p-nitrophenol was successfully converted into p-aminophenol using silver nanoparticle loaded microgel as a catalyst for reduction of p-nitrophenol into p-aminophenol. The value of absorbance at 400 nanometer that is associated to p-nitrophenol was measured as a function of time to monitor the progress of the reaction. And we carried out the catalytic reduction under various concentration of the catalyst. We used pseudo first order kinetic model for determination of the value of rate constant. For this purpose, log of AT over E naught was plotted as a function of time. It was noted initially the log of AT over A naught remains constant, and then this function decreases linearly with time, and again this function becomes constant. The time in which the log of AT over A naught does not change with the time is called induction period, and it is a well-known property of catalytic reduction of p-nitrophenol using polymer stabilized metal nanoparticles. We use this region from after induction period to the completion of the reaction. We use this region to actually measure the value of rate constant from the slope of the plot. So we use actually this plot for the determination of rate constant for reduction of 4-nitrophenol. This induction time can be explained on the basis of pathway of the catalytic reduction of 4-nitrophenol. Actually, reactant molecule diffuse from bulk region to the surface region, and they they take some time to reach the surface of silver nanoparticle. This induction period is actually associated time required to reach the reactant molecule on the surface of metal nanoparticles. Moreover, it was observed that the value of rate constant is a linear function of catalyst concentration, which indicate that the catalytic reaction is occurring on the surface of catalyst. This is the actual pathway for catalytic reduction of 4-nitrophenol on the surface of silver nanoparticles. The reactant molecules diffuse from bulk region and go to the surface region, then adsorb on the surface of metal nanoparticle. Then they interact with each other and are converted into product. The desorption of the product take place and reactant molecule diffuse out from interior region to the bulk region of the liquid. And in this way, we were able to successfully reduce 4-nitrophenol into 4-aminophenol, which is a useful green product. An other interesting feature of the catalytic activity of hybrid microgel is the tunable catalytic activity. We measure the value of rate constant for reduction of 4-nitrophenol at various values of temperature in aqueous medium, and the rate constant was plotted as a function of temperature. The value of rate constant was found to be increased initially and then decrease and again start to increase with increase of temperature. This sudden decrease in the value of rate constant is actually associated to the volume phase transition temperature of the microgel system. When we increase the temperature, the microgel system gets shrink. As a result, diffusion of reactant molecule to the catalyst surface becomes difficult. That is why the value of rate constant is decreased at a particular value of temperature that is associated to volume phase transition temperature of the microgels. However, after volume phase transition temperature, these nanoparticles may exposed on the surface and rate of reaction again start to increase with increase of temperature. So deviation from Arrhenius behavior is actually associated to the volume phase transition temperature of the microgel. So by using hybrid microgel, temperature responsive hybrid microgel, we can tune the catalytic activity of the hybrid microgel system. We use the Arrhenius equation for the evaluation of activation energy and Arrhenius parameter. For this purpose, we plot log of rate constant as a function of 1 over T before volume phase transition temperature and after volume phase transition temperature, and the value of activation energy was evaluated from the slope, while the value of pre-exponential factor A was evaluated by the intercept of the Arrhenius plot. We also used Eyring equation for the determination of activation parameter. For this purpose, log of K over T was plotted as a function of 1 over T, as shown in this figure, and the value of enthalpy of activation and entropy of activation was evaluated from the slope and intercept of Eyring equation or Eyring plot before and after volume phase transition temperature. The volume phase transition temperature the volume phase transition temperature of the hybrid microgel system was also evaluated to confirm that this decrease in rate constant is actually associated to the volume phase transition temperature. So value of volume phase transition temperature was evaluated using dynamic light scattering, and this value is perfectly associated to the lowest value of rate constant at a particular temperature. The Arrhenius and Eyring parameter were evaluated before and after volume phase transition temperature. The positive value of entropy of activation indicate that the process of activation is endothermic and entropy driven process. We have used the hybrid microgel system as a catalyst to degrade toxic chemicals into useful chemicals. For example, we were able to reduce 4-nitrophenol into 4-aminophenol, which is a green useful product. The smart polymer microgel system can also be used as adsorbent to remove highly toxic chemicals from aqueous medium. The methodology or approach is simple. We simply add the microgel system into the wastewater containing heavy metal ions. The metal ions present in the water go into the polymeric network due to electrostatic attraction between the negatively charged microgel particle and positively charged metal ions. Then these metal ions are adsorbed into the polymeric network. We can simply remove the metal ions containing polymer microgel by simple centrifugation, and we can get a pure water, and we can easily remove the heavy metals from aqueous medium using microgel as an adsorbent. So the recovered microgel system containing the metal ions can be treated in two different ways. We can remove the metal ions from the microgel system by changing the pH of the medium. And we can reuse the polymer microgel system as adsorbent again in the next cycle. Another approach is that we can actually reduce the metal ions into metal nanoparticle to obtain a hybrid microgel system, which can be used as a catalyst for degradation of organic dyes present in aqueous medium. We have reported both approaches in our different publications. For example, we have used a core shell microgel system as an adsorbent for removal of various metal ions from aqueous medium. For this purpose, we prepared a polystyrene and isopropyl methacrylamide and acrylic acid core shell microgel system with polystyrene core and the poly and isopropyl methacrylamide and acrylic acid shell. So we have a carboxylic acid groups in the outer region. We actually increase the pH of the medium by simple addition of a dilute solution of sodium hydroxide to obtain a negatively charged metal ions, negatively charged carboxylic acid in the network. These negatively charged microgel particles have ability to extract heavy metal ions or toxic ion present in aqueous medium due to electrostatic attraction between negatively charged carboxylic acid groups and positively charged metal ions. And the core shell microgel particle containing the metal ions can be removed from the water by a simple centrifugation method, and then these microgel particle containing the heavy metal ions were charged by HCl to displace the metal ions by hydrogen ions, and the system again is converted from negatively charged core shell microgel to the uncharged microgel particle, and this system can be reused as an adsorbent for removal of toxic chemical from aqueous medium. We measure the percentage removal of different metal ions using these microgel particle as an adsorbent at different values of pH and contact time. It was observed that the percentage removal can be increased by increasing the pH of the medium, that may be attributed to the conversion of uncharged core shell microgel particle to the negatively charged microgel particles. And the system was found recyclable with a maintained removal efficiency. Similarly, we used a microgel system for the extraction of copper ions from aqueous medium, and then we reduced the copper ion into the copper nanoparticle by using some suitable reducing agent. The resulting hybrid microgel system was used as a catalyst for degradation of 4-nitrophenol, methylene blue, and methyl orange. you have seen in the previous slides, the microgel system obtained by free radical precipitation polymerization have two problems. They actually have a very small size. So it is very difficult to recover the microgel particle after adsorption or after catalysis using a simple centrifugation. Actually, we need ultra centrifugation to recover the microgel system after adsorption or after catalysis. The other issue with such kind of microgel particle is the polydispersity. The particle size is not actually uniform in case of free radical precipitation polymerization. So the system is not much stable due to polydispersity. These both issues can be resolved if we use a microfluidic fabrication of the microgels. In fact, Dr. Goran has expertise in microfluidics, and our group has expertise in synthesis, fabrication, characterization, and application of microgel system. We are here together actually to join our expertise together to obtain highly monodispersed microgel particle with large size, with size in few hundred micrometer. So we have done a lot of work to join our effort to obtain a microgel particle system with large particle size and highly high monodispersity. As a result of this collaboration and joint work, we have done actually a lot of work, and we have published one review article as a joint research paper before going to start our collaborative work. For this purpose, we initially conducted a literature survey on microfluidic fabrication and application of microgel and hybrid microgel, and we have published it as a review article in Critical Reviews in Analytical Chemistry. We have also prepared a highly uniform hybrid microgel system containing the titanium oxide nanoparticles, and we have used this hybrid microgel system as adsorbent and photocatalyst for degradation of methylene blue in aqueous medium. This paper has been revised and its revision is under review and will be published, definitely will be published soon. We have also fabricated a polyethylene glycol diacrylate beads, and we used these beads as a microreactor to fabricate the silver nanoparticle into the microgel system, and we have used this hybrid system as a catalyst for reduction of 4-nitrophenol and methylene blue present in aqueous medium. This manuscript is ready for submission. As a proof, I am going to show some unpublished data just to describe that we were successful to address both problems. For example, we have obtained a highly monodispersed microgel system with coefficient of variance equal to 1.16%. You can see the particle formed by microfluidic fabrication method are highly uniform in size. They have very low polydispersity. The particle size is much larger than the particle fabricated by free radical precipitation polymerization. The particle size is in few hundred micrometer. These microgel particle can be easily recovered from the aqueous medium by simple centrifugation or filtration, or we can recover these microgel system by simple sedimentation method, because these particles have a large size and can easily settle down after extracting the metal ions from aqueous medium. Moreover, we were successful to fabricate silver nanoparticle in the outer region of the microgel particle, and we use this hybrid system as a catalyst for degradation of 4-nitrophenol and methylene blue present in aqueous medium. In the end, I am grateful to the Director Institute of Advanced Studies, Loughborough University, and her team for supporting me under IAS Open Program. I am also thankful to Dr. Goran for inviting me and facilitating me to carry out this project. I am also thankful to the Director Center for Physical Chemistry and Head School of Chemistry, University of the Punjab, for relieving me from my duties to visit Loughborough University. Thank you very much, all of you, for your attention.